We've been talking about trees, and now we're going to talk about tree traversals. Let's remind ourselves what that word traverse means. If we look it up in the dictionary, it says one of the definitions is to pass or go over, or back and forth over something, to cross. So if we're talking about a tree traversal, we're talking about how to pass along the tree, or how to go over, how to visit all of the vertices within a tree. So that's what a tree traversal is, different ways that we can traverse a tree. Now, information often is stored and organized in the form of a rooted tree. So here's some examples here on our computers. We have files saved within folders. Those folders can have folders within themselves, and so we've got a tree situation here. So here we might have a folder called Documents, and within the Documents folder we have some other folders, and within some of those folders we might have other folders. And then if we were trying to search through those folders, we would need to have a systematic way to visit all of those folders and search each one. So we would need to decide how we want to traverse that tree. Over here on the right, you see we have a diagram of the solar system. Lots of things are easily organized in the form of a tree like this, where we start with a main category and then we break it up into some different categories, and those categories can be broken up. Now let's say that we have some system like this, and we want to print out all of the different what each of these different what we would consider vertices have in them. If we want to print all of that out, then we would have to decide how to traverse this tree in order to visit each one of the vertices and then print that information out. So that's another example of why we might want to know, talk about different ways we might traverse a tree like that. So when we have to process information in a tree, as I said earlier here, that sometimes it might be searching through files, or we might want to, when we're processing information in something like this solar system tree, maybe we want to just print it out. Or maybe we're reading a book and this is how the book is laid out, and we're trying to decide how we want to go about which order we'd like to read that book. So that's another example. So anyway, when information in a tree needs to be processed in some way, whether we're searching or printing or whatever, then there needs to be a way to systematically visit each vertex, and that would be called a tree traversal. So as each vertex is visited, the processing step would be performed. And so that could be either, this says a computation or outputting some data. In our examples here, processing step for the computer would be searching through that folder for whatever we're looking for. Now there are two different systems that can be used to make sure that every vertex is visited within a rooted tree. The first one is pre-order traversal, in which a vertex is visited before its descendants are visited. But in a post-order traversal, a vertex is visited after its descendants are visited. So let's say that we've got our computer has this organization here where we have these folders here, and let's say that we want to do a search through your computer files. Then if we were doing a pre-order traversal, we'd say, let's look in Documents first, all of the files within Documents. Then let's look at all of the files in CS211, then in 255, and then after 255 we'll go deeper into 255 and look in Labs and Notes, and then go on to Math 241. That would be considered a pre-order traversal, because notice we didn't even search in Labs until we'd already searched in the folders above it, CS255 and Documents. So that would be, again, called a pre-order traversal. Or we could do it this way. We could kind of basically think about it as going to the ends of the branches and then starting there and then going back up. So we could say, okay, starting on the left here, we see we can go as far as we can to CS211 and we could search there. Then in the middle, we go as far as we can down to labs and notes. We'll search there. Then we'll go up and search in CS255. And then we'll go on to the right to Math 241. And then eventually, at the very end, we'll search in documents. So that would be considered a post-order traversal because each vertex was only visited after all of its descendants were visited. The book lays out the pseudocode that would be needed in order to go through those different types of traversals. So here's the one for pre-order traversal. And remember what a pre-order traversal is. A vertex is visited before its descendants. Now we're going to just go over this just to see if it makes sense. You won't have to come up with this or anything, but I think we should just look at it and make sure that it does make sense, that this pseudocode would accomplish what we're wanting it to accomplish. So this is going to be a algorithm called pre-order, and we are going to start with calling a function called process_v. Now we can have anything in there. Maybe we're going to search through that folder, or maybe we're going to just print something out. So that's what this process is all about, is just processing it, whatever that means, okay? So it's going to process a particular vertex first, see this? And then it says for every child W of this vertex, we will call this algorithm again. So here we're calling pre-order again for that child of W. So then this will all be called again, and the child will be processed, and then all of the children in it will be looked at, and then this entire algorithm will be called for those children within the children. So you see that the fact that the process here, this red statement here, is at the beginning before the loop, before looking at all the children, it makes sense that that would be the pre-order traversal. But over here, here's the pseudocode for post-order traversal. And remember there, the vertex is visited after its descendants. So visited in this case again means, as before, it means processing it. So that might be searching through a folder or printing the title of a chapter or something like that. So for the post order, we're going to call this algorithm post order. And notice that we start at some vertex again, and then it would be normally if it's a rooted tree, which it would be, then we're going to start at the root, and then for every child of the root, we're going to call this algorithm again. So notice we don't process V until all of the children of V have been this has been called for all of the children of V, and so and then each child of V would not be processed until all of its children are processed. So the fact that we have this red statement at the end, process V, way at the end there, means that the processing is not going to be done until all of the children are taken care of. So that would be the pseudocode for the post-order traversal. Now, how do we go about finding the different traversals of a tree? So what it would just be a list of the order in which we would visit the vertices. Okay, so we're just going to put some order of the vertices. We want to make sure that we go through the entire tree and visit every single vertex. Okay, so how would we come up with the pre-order traversal of this tree here? We see this tree here, the root is at A, and then we see all of the different vertices below that. Okay, so here are the instructions. So let's start by the first, and again, this is for the pre-order traversal. So the first instruction says draw an outline all the way around the tree, which is shown in orange. So see how this orange outline has been drawn for us. Okay, now the next step is to, starting at the root, move to the left. So we're always going to move to the left here. Follow the outline all the way around the tree. When we pass the left side of a vertex, we say that we would visit that vertex. So, we're going to, if we're processing something, if we're searching that folder, or if we're printing the name of that chapter of the book or something, then we would do that as we pass the left side of the tree. So let's start here. Again, we're going to start at the top and we're going to move to the left. So as I move, I'm going to go along this outline, and as I move to the left, and here I've moved to the left of A. So that means I'm going to process that, visit that, or again, we could say we're processing it, but let's just call it visiting here. So we're going to visit A. So A would be the first one visited, so I'm going to put A on my list here. Now let's continue on along the path, and now I'm to the left of B. So I'll visit B. So I'll put B there on the list. Come down here. Now I'm to the left of D, so I'll put D on there. Now I continue along here. So I need to continue along here. I'm to the left of these, and I've already processed them anyway. So now I come here. Now I'm to the left of C right now, so I would visit C. Now I come along here, I'm to the left of E, E comes next, then now G, now F. Yes, I didn't make G come up there, so G is on there, now F comes on there, and then I'm done. Okay, so as I followed along that outline, as I was to the left of a vertex, that's when I would say that I'm visiting it. So how about this? If we've got some folders, how would we do this? Again, we will start by drawing an outline around the tree here. And we're going to go to the left. And so we'll start here, and as I visit the left side of a folder, I will say that I'm actually visiting that that vertex. So here I'm to the left of documents. So documents would be the first one I visit. Then I come here. Now I'm to the left of CS211, so I would be visiting that next. Now I come up here, I'm to the left of CS255, so I'm going to visit that. I'm to the left of labs. I'm now to the left of notes. Now I'm to the left of Math 241. And I'm back to the top, and I've visited all of the vertices. So that is pre-order traversal. So this is a pretty easy little method to be able to find the order of a traversal here. And this one again is for the pre-order. We have another little trick for post-order, and that's the same, except that we're going to say that we are visiting the vertex when we get to the right of the vertex as we move along again that outline. So we're going to start at that outline, draw the outline first, and then start at the root, moving to the left again, and then follow the outline all the way around the tree. When we pass the right side of the vertex, we will say that we're visiting it. So I start along here, and notice I'm not to the right of A, so I don't visit A yet. And I don't visit B. Now, I'm finally to the right of D, so I would say that I'm going to visit D. Now I'm to the right of B, so I'll visit B. Okay, now I come along. I'm to the left of these, so I don't visit them. C, E, G. I'm to the left, so I'm not going to visit them, but now I'm to the right of G. So G will be visited next. E comes next. F, C, and I go up to the top, and then finally I visit A. A was visited after everything else was. And so if you take a look at all of these, every vertex that gets visited after all of the children are visited. Okay, let's look at the folder situation here. Again, imagine that outline. I'll not draw it until we actually start moving along it. And we will again go to the left. This time though, again, we're going to say that we're not visiting that until we're to the right. So I'm not going to visit documents yet. Now I'm to the right of CS211. So I'd say I'm visiting that. I'm to the right of labs. To the right of notes. Now I'm to the right of CS255. Now I'm to the right of Math 241. And finally, I'm at the right of documents. So that would go last. So that's the trick there. So these are really, as you can see, pretty easy. It might be, I don't know, it might have been a little harder if we didn't have this trick, especially if it got really, if it was a really big complicated tree. But with this trick, you can easily come up with the pre-order for the, when we're looking at the left side, when we're visiting a vertex, when we're at the left side, that would be the pre-order. When we do it on the right side, that's the post-order. Okay, let's just look at some more examples here. I think you could do this pretty easily. I'm going to go ahead and put what the pre-order would be, and just let's just look at it real quick. We're going to draw as I go. For pre-order, remember we're supposed to visit it when we're on the left of it. So I'm just going to, you see here I already have it E, A, B, D, C. But as I draw along here, I'll mention the vertex when it's time to visit it. So start again at the top, okay? E, A, B, D, C, and I'm done. Okay, now post order is this one here, and I'll go around that outline again and mention the vertex when I get to the right side of it. So start here again at the top. Finally, B, D, A, C, and E. Now let's do this other one here. It's going to be EACBD. So let's try it here. Again, pre-order on the left side. E, A, C, B, D. And we'll do post order. I'll go around again. This time it's when we're on the right side. A, B, D, C, E. Here's one more example, but I think you get the hang of it, so we won't bother to go over this right here, but it is another example that you can look at on your own and make sure that you end up getting what I have here. And if you want some more practice, then there is an additional exercise there in this section that you might want to look at. That's exercise number 1, and I've opened up the solution, so you should be able to take a look at that and try that out for yourself. Now let's move on to a new section, and this section is on spanning trees. So what is a spanning tree? A spanning tree of a connected graph G is a subgraph of G which contains all the vertices in G and is a tree. Okay, so it's going to be a subgraph of the original graph G. We want to make sure that all of the vertices are contained in this subgraph, but we want to make sure that this subgraph is a tree. And remember, what that means is we can't have any cycles in there. So we're not talking about rooted trees now. We're kind of back to talking about the free trees. So here, if we look at this graph on the left, we could call that G, say that is our graph G, and let's come up with some subgraphs of G that would contain all the vertices, but can still be considered trees and not have any cycles in there. So you see that these are 3 different possible spanning trees. The red marks the actual subgraph part. And of course, that I haven't made the vertices red, but of course the vertices would be part of these subgraphs here. So you see that in each case, all of the vertices have been visited, have been included, and there are no cycles. So what might be an example of this, an application of this situation in real life? Well, let's say that we've got a computer network and we've got a bunch of computers in this network and we need to broadcast information to every computer. Okay, then we could look at this network as we could look at this network as an actual graph, and the different communication links between any of the computers would be represented then by edges there. And so what we would need to do is maybe draw an example, draw a map of what this network would look like, where we have all of the different links that in there and all of the different computers listed. And then we would need to find a way that we could make sure that we have a subgraph where we include every vertex. Now, why wouldn't we just say, oh, we'll just let it, go, just use the whole entire graph? Well, the goal would be to minimize overall congestion. So it'd be wasteful to have more than one path going from one computer to another, let's say. So we don't want to have any cycles in there, which would give us more than one path along from one computer to the other. So by coming up with a spanning tree, we would be making sure that we're taking care of that we're getting to all of the computers, but we don't have any cycles in there to cause more congestion than would be needed. How would we create a spanning tree once we're given some graph that we might call G? Well, there's a couple of different ways that we can go about it. We can use depth first search, which favors going deep into the graph and tends to produce trees with longer paths from the start vertex. Or we might choose the breadth first search. That explores the graph by distance from the initial vertex, starting with its neighbors and expanding the tree to neighbors of neighbors. Okay, so we're going to look at a lot of examples and get the idea of how this works. But the book gives a good analogy, which I think really helps us when we're trying to create a spanning tree one of these two ways. The book says this: if you think of each algorithm, the depth first or the breadth first, as an explorer who is visiting each vertex in a graph. The DFS explorer, that's depth first search, that explorer sets out along new paths, always looking to go far beyond her starting location. We're always starting with one particular vertex, okay? And then, so this explorer is going to say, oh, let's go to a new vertex, and oh, let's go to another one. Let's go to another one, never really caring, how far she gets away from the starting location. But the BFS explorer, on the other hand, is more conservative, favoring locations close to her initial location before venturing beyond. Okay, so that explorer would then be, let's look back to the definition of breadth first search. Explores the graph by distance from the initial vertex, starting with its neighbors. So she would go to all of the neighbors of the initial vertex first, and then start it with those, and then go to the neighbors of the neighbors, but still, trying to stay as close as possible to the initial vertex, and just searching in that order. Neighbors first, and then neighbors of neighbors. Now, in both of these, when we come up with when we're trying to come up with a spanning tree, we're going to follow some rules. In all of these examples here, we're going to have the vertices labeled alphabetically, like A, B, C, D, okay? Now, if you would be given a graph that's not labeled, then you would just need to label the vertices with alphabetical names, so A, B, C, D, and so on for the vertices. Okay, so when we are starting with vertices that are already labeled like that, we're always going to start at the vertex that's labeled A. Okay, so we'll start at A, and then we're going to follow these rules in both cases, but sometimes we'll have a choice of vertices at any given point. We're following the rules of either depth first or breadth first, but we see that we could go a couple of different ways. If we have a choice, we're always going to choose the one that comes, the vertex that has the label that comes first in the alphabetical order. That's so that we can all get the same answer. Make sure that we're all following these same rules and getting the same answer. That way you can make sure that if you get the same answer that the book gets, or the same answer that I get, you know that you followed these rules correctly. So here we start with a graph. We see the same graph on the left and on the right. On the left, we're going to come up with a spanning tree that is found by using depth first search. And on the right, we're going to find a spanning tree using breadth first search. So let's start on the left doing depth first search. And we're going to again start with A. Now remember what this is, depth first. It says going deep into the graph tends to produce trees with longer paths from the start vertex. So let's start with A, and we would do this. Here's what we would do. We'd say, okay, let's, from A, I could go to B or G, but that rule says to choose the vertex with first in the alphabet, so we would go to B. Now, this explorer does not care about staying close to home. She's going to say, okay, I'm at B. Now where can I go? Well, I could go to C or G, but she'll go to C because that's first in the alphabet. But now she's at C. Okay, now she can go D, E, or H, but again, she'll choose D because that's first in the alphabet. Notice there's no concern about staying close to home. We've gone as pretty much as far away as we can right away. Not that the goal is to get far away, but it's to go from vertex to vertex, not caring how far away we get from the start. Now notice when we get to D, there's a problem, and that is we're at a dead end. It's okay to have a dead end. We'll just backtrack to the the vertex right before it and see if there's a place we can go from there. So since we can't go anywhere from D, we'll go back and look at C. Is there a vertex we could visit that hasn't been visited before from C? Yeah, we could visit E or H. So we will choose E. Now, from E, we can only have one way to go, and that's to F. So we'll go ahead and visit F. From F, we can choose G or H. I will choose G since it comes first. Now, again, we're at a dead end. Now, you say we're not really at a dead end, but we don't want to go from G back to A, right? Because that will give us a cycle. We need a tree, and a tree does not have a cycle. So we don't want to go from G to A, and we don't want to go from G to B. Because for one thing, that would make the cycle, but for the other thing is we've already visited A and B, so there's no need to visit A and B again. So there's just one vertex that has not been visited, and that's H. So we're at G, kind of at a dead end, so we would have to go back to F and see what we could do from F. And yeah, we could visit H from F, so I'll mark that, F to H. And now we can double check and see that we've visited all the vertices, and what we ended up with those red edges there, along with the vertices that are on those edges, would be a tree. Now let's go on to the breadth first search. This one might seem a little bit more complicated. Once you do a few examples, it's not too hard, but at first it might seem a little confusing. Now I'm going to follow the same rules as the book follows, right? So what we're going to get for our answers is the same answers that the book would get if they had these problems and these graphs, and I think a lot of these graphs do come from the book. So we're going to get the same answers. However, I'm going to, this breadth first search involves keeping track of a little list, kind of a to-do list, where I want to go back and visit next. Okay, so that you have to create this little list using this breadth first search. And my list is going to look a little bit different than the book's list. I think the way the book does it, it's for one thing, I think it's a little harder to follow. I think, and also the way the book does it, you aren't keeping. I'll tell you when we get there, but there's some information that you're not keeping that you would need to know. So I think my way works a little bit better. Again, we get the very same answer. We're really doing the same thing. It's just a matter of what we're putting into the list, how much information we're putting into the list, okay? Okay, so I'm going to put a list over here because, again, that's a big important part of the breadth first search. But again, I'm going to start with A, and again, I'm going to just say, where can I go from A? I could go to B or G. I'm going to go to B because that's first in the list. Okay, now remember, we don't want to go far from home in the breadth first search. So the best thing to do here then would not go from B to C, but actually go from A to G, right? Because I'm starting with A, so I want to visit all of A's neighbors first before I go any further. So the next logical thing to do would be to visit G. But before I go on to G, here's what I want to do. Every time I visit a vertex, like I've done here with B, I want to make note of the neighbors of that new vertex. So say, well, B, what are B's neighbors? Well, B has two neighbors, C and G. So I'm going to kind of keep track so that I can once I take care of A's neighbors, then I want to go on and take care of B's neighbors, okay? So I'm going to keep this list as kind of like a to-do list to come back to. So once I go from A to B, I'm going to say, well, now B has a neighbor C. So this is how I'm going to list it. I'm going to say, I'm just going to put a little arrow. B has a neighbor of C, or B would go to C. Now, the way the book would do it would just put a C there. But that doesn't show how we get to C, and sometimes there's more than one ways to get to C. So by the time you come back to that, you're wondering, well, how do I get to that? So anyway, that's my difference is I'm this list, I'm doing it from top to bottom, whereas the book does from left to right. And I'm including this little extra thing here with the B and the arrow saying I can get to C from B. Okay, so but that's my to-do list to come back to once I'm done with all of the neighbors of A, because I don't want to go on to neighbors of B until I've visited all the neighbors of A. Okay, so I've just visited one neighbor of A, that was B. I took note that B has a neighbor. Now I could say, well, B also has a neighbor G. Shouldn't I put that down on the list? No, because G gets taken care of right now. G is a neighbor of A. So we're getting that taken care of right now. We have both of the neighbors of A are taken care of by marking those edges as red. So what we did was we marked both of those, but when we marked the one to B, we put on our list, well, yeah, let's not forget to go back to B's neighbors, any neighbors that it has, and it has C. We're not going to list G because G's already been visited. And remember, our goal is just to visit all of the vertices. But so when we visit G just now, I marked A to G there as red. Now we take note of G's neighbors. Every time we visit a vertex, it's not that we're going to necessarily go there next, but we're going to put that on our list. So G's neighbors I'm going to put on the list next. I'm going to put it right below. So I would say that, okay, I want to take note and remind myself that G has a neighbor I want to get to fairly soon. Not right now, but fairly soon. Okay, so I'll put G has the neighbor of F. So far, what have I done? All I've done is I've visited just the neighbors of A. Okay. Now, I'm not going alphabetically or anything. I wouldn't say, now let's visit the neighbors of B because B comes next in the alphabet. That's not what we do. But now, once we've visited all of the neighbors of A, which is, again, we just start with A all the time, then we start looking on our list. What do we have on our list to look at next? Because these were ones we want to get to soon, because these are neighbors of neighbors, and they're closer to A than something else might be, right? So let's start at the top and say, let's look at that. We remember that C was a neighbor of B. So watch what I do. I'm going to cross that out of the list because that was on the list, but now I've taken care of it, so I'll cross it off. And then I've put the line there, B to C. I wanted to come back, and now I have. Okay. Now, again, I'm going to not go on to C's neighbors, but I'll at least put on the list what C's neighbors are. C has a neighbor of D, C has a neighbor of E, and C has a neighbor of H. Okay, so those are things I might come back to, but I'm not going to do right yet. Okay, now once I've done that, let's see. So I did the B to C, and I did that, and then I took note of all of these neighbors of C. The next thing I do again is go to the list. What's at the top of the list now? It's that G has a neighbor F. I noticed that a while back, but now it's time to go and take care of that. So I'm going to cross out G to F on the list and then mark that edge as being part of the tree. Okay, so G to F now is red. Now, because I visited F just now, I need to take note of F's neighbors that I would need to worry about once it's time for that. But let's look at the neighbors of F. Again, G is a neighbor of F, but it's already been visited. We have neighbors H and E of F. But before we put that on our list, let's see if H and E will already have been visited if I use something else above in the list. It looks like H is going to be visited from C, and so is E. So E and H are already on the list to be visited. So we don't need to add them onto the list. Okay, so I don't have to add any of F's neighbors onto my list because they're already going to be taken care of. So now let's go back to the top of our list. What's next? C has a neighbor of D. So I'm going to go ahead and mark that out, put that there. Does D have any neighbors I need to worry about? No, so nothing new goes on my list. Now C has a neighbor of E. That's on my list, so I'll mark that. Now, does E have any neighbors that I haven't taken care of yet? No, everything's okay for E. Both of its neighbors have been visited. Okay, now one more in my list. C has a neighbor of H. So I'll mark that. And H, I don't have to worry about any of its neighbors because all of them have been visited. Okay, so what have I done? I have now created a spanning tree. I've visited every vertex here. Now with spanning trees, let me say this, I didn't say this yet. I want to make sure that you understand with spanning trees that we're not worried about like with the traversal, we're saying, which order are we visiting these. With the spanning tree, it's just going to be a tree. There's not going to be a list of, I'm not going to have A, B, C, E, F, anything like that as my answer. My answer for a spanning tree is just the subgraph, okay? So, and we're just coming up with a tree. We're not worried, even though you might say, well, we are kind of visiting these in a certain order as we come up with the tree. That's true, but it's just that we're doing that to come up with the tree. But the answer is just the tree itself, not that, oh, we're going to go in this particular order at any time. Okay, so hopefully this makes sense. We're going to do more examples. So by the time you see all of the examples, hopefully it'll all be making even more sense. Okay, here's another graph, and we're going to find a spanning tree each way. Depth first search and a breadth first search. So depth first, again, we start with A and we say, where can we go from A? Well, there's several options, but C comes first in the alphabet, so I'm going to go A to C. Now, where can we go from C? We can go B or F, but B comes first in the alphabet, so I'll go to B. Now from B, where can I go? I can go to E or I can go to F. I'll go to E since that comes first in the alphabet. Now I'm at a dead end, so I'll just go back to B and figure out where I could go now from B. Well, I can go to F. Remember, we're not going to ever go back to anything that's already been visited, so I'm only looking for vertices that haven't been visited. Okay, from F I can go to D. And from D I can go to G. And that is my spanning tree using depth first search. Be sure and don't go back from G to A because now you've created a cycle. And this is all we need to make sure that we visit all of the vertices. Okay, now let's go on to the breadth first search. And remember, we're going to have a list for that. So I'm going to start a list over here and have that ready to go. Okay, so again, we start with A, and we say from A, we want to visit all of the neighbors of A. So I'm going to end up visiting C, F, D, and G. Those are going to be my first, so I'm going to have red coming out of A at every one of these edges from A. Okay, but as I do that, as I draw an edge, I'm going to take note of the neighbors of these new vertices so that I can come back and do those as soon as I can after I've taken care of all the neighbors, so that, for whichever vertex I'm at. Okay, so I'm at A, so I need to take care of all of the neighbors of A. So I'm going to say that I'll start with A to C, and C has a neighbor of B, so I'm going to put that on my list. I don't want to go there yet, right? Because I have to take care of all the neighbors of A first. So I'm not going to go to B, but I'm going to put that on my list. And again, what differs between the way I'm doing it and the way the book's doing it, the book would just put a B there instead of C has a neighbor of B. And the reason I'm doing that again is so that we know how to get to B, because sometimes there's more than one way, and I want to keep track that I'm going to get to B through C and not through a different vertex. Okay, so that comes sometime. I'm going to do that. As soon as I visit all the neighbors of A, then I'll do that. Okay, now you might say, well, C also has a neighbor of F. Shouldn't I put C as a neighbor of F on my list? But F is also a neighbor of A, and remember, we're going to be visiting all of A's neighbors right now. So F is going to get visited right away. So I'm going to visit D next, because that comes next in the alphabet. Now, does D have some neighbors I need to put on my list? Well, again, the neighbors of D are also neighbors of A, and I know that my neighbors of A are going to get taken care of right now. So I don't need to put that on the list, because F and G will be taken care of right away. So the next one would be F, and so I'll mark that. Now, what about F? Does F have any neighbors that I need to put on my list so that I can visit those later? Well, I would say B is a neighbor, but I already have B on my list, so I don't need to put that. Okay, and C, we definitely don't want to put that on our list because C's already been visited. Okay, so now we have one more neighbor to visit from A, and that's G. So I'll mark that, and I'll think, does G have any neighbors I need to put on my list? And no, because it has neighbors, but those neighbors have already been visited, so I'm good there. So I've now run out of neighbors of A, and that's where I started, just finding neighbors of A. So the next thing I do then is look on my list. So I go on the list and say, what was I supposed to come back to? Oh, well, I see that C has a neighbor of B that I wanted to come back to. So that would be next. So I'll go ahead and cross that off of my list and put it here. And when I put that there, I've added a new vertex in there. So I'm going to make note any of the neighbors of that new vertex that needs to be visited soon. And B would have a neighbor of E that needs to be visited soon, so I'll put that on my list. F, of course, doesn't need to be visited. It's already been visited. Okay, now we would still then be looking for the next thing is we'd be looking on our list. If there were more things on our list to do next, we would do those next. But it turns out that we didn't have anything more on our list. We didn't have anything on our list before the visiting E. So we're ready to go ahead and cross that one off too. So B has a neighbor of E. I'll go ahead and visit that now. So this would be our breadth first spanning tree. Maybe let me just do this and I'll go over it very quickly. Again, I just want to go over this breadth first one more time. So we start with A, And so, as I said, I'm going to do this quickly so that you kind of get the idea. I'm going to visit all of A's neighbors, but as I visit a neighbor, I'm going to see if there's neighbors of neighbors I need to come back to. So I visit C and make note that there's a neighbor I can visit. Now I visit D, no neighbors to be visited to put on my list because all of the other neighbors here of D are neighbors of A that we're going to get to right away. Okay, F. Now what about F? Is there a neighbor I need to worry about, put on my list? No, because B's already on the list. And then A to G, that's another neighbor I visit. And G doesn't have any more vertices to worry about. Okay, so I've just visited all of the neighbors of A. Now I go to my list. My list says that B is a neighbor of C, so I should go to that next. So I put this one here. B is a neighbor of C. And then as I do that, I'll check and see, is there a neighbor of B that I need to put on my list? Yes, I would put that E is a neighbor of B. And I would go do anything else on my list next, but nothing else is on my list. So now it is time to go ahead and take care of that last one. B goes to E. Okay, and that's how I get the breadth first. I have two more examples for you. Here's one of them. So here I have a graph. I've got it down there twice, and we're going to find the spanning tree using both of these methods, depth first and breadth first. So let's start with depth first again. We're going to start with A, and we're going to visit all, no, we're not going to visit all of A's neighbors. That's what we do in breadth first. So we're going to just find a place to go from A. So we're going to go to B. Then from B, where do we want to go? Let's go to C. From C, where should we go? Well, let's go to D. Now, we don't want to go from D back to B because that would give us a cycle. So we'll go backtrack until we do have another place to go. Go back to B, and now we've got somewhere else to go. We can go B to E, and then from E we can go to F. And now we have now visited all of the vertices. So that would be what we would need there. So again, just go from one to the other, not caring about staying close to A. Okay, breadth first. Here we're going to have a list, and so I'll have that ready here. And now again we start with A, and remember for breadth first we're going to visit all of A's neighbors first. But we're going to put on our list any neighbors of the neighbors that we want to come back to. So we're going to go from A to B. We'll mark that, but let's keep track. Are there some neighbors of B that we need to take care of? Yeah, B has a neighbor of C. B also has a neighbor of D. So we'll put that on our list to come back to. Now we'll say, what's another neighbor of A? Because again, that's where we're at right now. E is a neighbor. There are no neighbors of E that are not already neighbors of A, so we don't have to put anything on our list for that. F is also a neighbor of A, so I'll take care of that. So I've taken care of all the neighbors of A, so now I'm ready to look at my list. This says that C is a neighbor of B. So that's the one at the top, so I'll do that next. C is a neighbor of B. Now I could say, does C have any neighbors I need to visit? And I might say, well, D is a neighbor, but D again is already on my list. So I don't need to put that D is a neighbor of C because D I already know is a neighbor of B. And see, this kind of shows why I do the arrow thing here, is because if I just put a D on there and I came back to this and said, okay, now I need to visit D and just had D, I wouldn't know whether to visit D from C or to visit D from B. And if we're doing breadth first, we want to do it the right way, and that would be visiting D from B. So that's why I have this little extra in my list here. So I go to the list. B has a neighbor of D, so I will visit that next. And now nothing on my list is left, and looks like I visited all of the vertices, so I'm good. Now I do want to just read this. We've been talking about breadth first and doing these examples, but the book kind of talks about this, has this process, talks about this process in a little paragraph. And we've been doing it, but I thought, I should talk about it somewhere in the slides, put it down there as here's what we've been doing. Here's the process we go through. And I changed it a little bit because instead of the book saying, left of on the left of the list, on the right of the list, I said top of the list, bottom of the list, because my list is going bottom to top. So anyway, changing just that, here's what we could say is our process that we've been going through on the breadth first search. Breadth first search visits vertices in the graph according to the proximity to the start vertex, which is vertex A. The algorithm maintains a list of vertices to be visited soon. Vertices are added to the bottom of the list, and the next vertex to visit is taken from the top of the list. So that's kind of what we've been doing. Here's our last example. So let's start at A, and we're going to do depth first search. So A would go where? Well, A can go several places, but we'll have A go to B because B comes first in the alphabet. Now from B, where can we go? Well, B could go to D next, right? Then from D, where could we go? Well, we could go to either C or E, but we'll go to C. Now, C could go to E, because E comes next. Now, E, we're kind of now at a dead end. We don't want to go back to D, right? Because that would give us a cycle, and D's already been visited. So let's go back to C and see, is there somewhere we could go from C? Yeah, we could go from C to F. Now, from F, we could either go to G or H. We'll go to G since that comes first in the alphabet. Now, from G, looks like D and B have already been visited, so the only thing that needs to be visited now from G is H, so we'll go from G to H. Okay, so the explorer has walked around and just gone from one to the other until it got through everything. Okay, now let's go breadth first. So I've got my list ready to go, and I'm going to start at A. A can go, from A we want to visit all of A's neighbors. So we need to visit, we're going to draw the edges red between A and B, A and C, and A and D, right? But as we draw those edges, we want to take note of some neighbors of those new vertices that we can visit soon. Okay, so I'll go A to B. That's the first neighbor we would visit, and on our list, let's mark down some neighbors of B that we want to make sure and visit. Well, F is a neighbor of B, and so is G. So those are two that I'll put on my list to come back to after I've visited all the neighbors of A. Okay, now I'll visit C, A to C. Now, what about that? Are there any neighbors of C I need to take note of? Yeah, E. E would be a neighbor of C I want to come back to. Okay, now I still have one neighbor to visit, and that would be D. And that one, for D, I might think, well, yeah, there's a neighbor of E and G I could put there, but I'm not going to put those down, right? Because E and G are already on my list. So I wouldn't add any more once I visit D. Okay, now I have visited all of the neighbors of A, so now it's time for me to go and start doing things off the top of my list. So this says B has a neighbor of F, so I'll mark that off of the list and mark that edge as red. Now B has a neighbor of G. I'll mark that up. Oh, sorry. before I go to G, I need to make note that F has a neighbor of H. So I need to mark that down. So F has a neighbor of H that I'll put on my list. Now I'll go back to um, the taking care of B to G. So that's on the top of my list, so I'll do that now. So B can go to G. So I've added G into the tree. And then I would say, does G have any neighbors I need to keep track of? But H is already on the list, so I don't have to add any more. Okay, so the next one is C has a neighbor of E, so I'll go back and do that one next. And E has no more neighbors to worry about. Then I'll go back to my last entry on my list, and that's F goes to H, because F has a neighbor of H. So I'll mark that off, and I'll mark that edge as red. Now I have visited all of the vertices, and it is a tree. I don't have any cycles, so I've come up with a spanning tree for that one using breadth first. Now I thought you might like some more practice in creating these spanning trees. So what I decided to do so that you would be able to practice and yet be able to also check your solution with the correct solution is I decided to put these same examples that we just did on these last two slides. So here's the first two examples, and then on the last slide I have the next two examples. So for each one I've got the graph there twice, and I don't know if you want to print these off or just take a look at them and then write the graph on a piece of paper and then go through these, finding the spanning trees both ways for each of these examples. And so I have those here so that you can do that on your own. Then you can check back in the notes or back in the video, check your answer with what I came up with and see if you get the same thing. Okay, so here's two problems here that you can work on and then check with my solution, and then the last two also. So I would say go ahead and try those just to make sure that you really have this process down.